So in the last video, I showed you how to use a Laplace transform by going from basically a domain where we're talking about differential equations to a domain where we're talking about algebraic equations. But I didn't actually define the Laplace transform for you, or to show you how to compute it. So right now, I'm going to show you what the definition of a Laplace transform is. So say we have a function of t, which we'll call f of t. Then the Laplace transform of f of t, we'll just call that capital F of s, just like last time when I gave you little y, we got y of s. So whatever is in here, whatever the name of the function y, f, we'll call it capital F. And this is the definition. The integral from 0 to infinity e to the minus st f of t dt. Now, looking at this is the sort of indefinite integral that you would have studied in Calculus 2. Remember the meaning of when you have an infinity up here. What this means is you have the limit as b goes to infinity of the integral from 0 to b of e to the minus st f of t dt. So you just do a regular old integral from 0 to a number which we call b, and then you let b go all the way off to the right, all the way to plus infinity. And this is the definition of the Laplace transform. And if you take a look at this, since you're integrating with respect to t, by the time you get finished with this, there's no t left. The only variable left is s. So I want to give you an example. Let's say f of t equals e to the t. So we are going to take the Laplace transform of the function y equals e to the t. According to the definition, this is the integral from 0 to infinity, e to the minus st times e to the t dt. And we know what to do with the inside bit here. We're just going to do some algebra here. When you multiply powers with the same base, you add the exponents. So 0 to infinity, e to the minus st plus t. We can factor the t out from that. So we have minus s plus 1 times t dt. Again, if you multiply this together, you have minus st and then t. So those two are exactly the same. And as I said, this is really the limit as b goes to infinity of the integral from 0 to b of e to the minus s plus 1 t dt. And so it's time for us to go ahead and take an antiderivative inside. So limit as b goes to infinity, we want, let's see, t goes from 0 to b. These limits over here. Now let's take the antiderivative. The antiderivative of e to a number times t is 1 over the number times the original function. So 1 over minus s plus 1 e to the minus s plus 1 times t. And let's continue that over here. So equals, so the limit as b goes to infinity. If I plug the b in, I end up with 1 over minus s plus 1 times e to the minus s plus 1. We're going to put b in for t. Minus, if I plug 0 in for t, 1 over negative s plus 1 e to the minus s plus 1, but really who cares, times 0, so e to the 0. Now think about what happens as b gets very big. It kind of depends on what minus s plus 1 is. If minus s plus 1 is negative, then as b gets very big and positive, this whole thing gets negative. So if s plus 1 happens to be a positive number, in other words, if s is greater than 1, then, sorry, if s is greater than minus 1, then s plus 1 is going to be positive, minus that's going to be negative, and as b gets very big, this whole thing goes to 0. So we are going to take this is going to be the part that's going to sound a little bit fluffy right now because I'm not explaining. We're going to take s to be only on the domain where it's greater than 1. That's because we want this piece to go to 0. If this piece doesn't go to 0, it blows up to infinity, which is no good. So this thing's really only defined, I guess I have explained it pretty well, this thing's really only defined if s happens to be greater than negative 1. And so this whole part goes to 0 as b gets very big. And so what we have is minus 1 over negative s plus 1 times e to the 0, which is 1. I'm going to distribute this minus sign in. And so what we have here is 1 over s minus 1. So the Laplace transform of e to the t is equal to 1 over s minus 1, so long as s is at least as big as minus 1. And as I promised, there's no more t here. We started off with a function of t. We put it inside this L thing and chug, 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 chug. And by the end, there is no more t. We just have it in terms of s. So we've gone, if you remember what we had in the last video, over here we had the differential equation. If there was an e to the t over there, when we took the Laplace transform on this side, we replace it by a 1 over s minus 1. Now, I want you to take a look at page 317 in your textbook and look at line 2, and you will see the Laplace transform for e to the alpha t. And you will see it's consistent with what we have right here. So if you're worried about having to do a lot of these integrals, don't. Mostly what we're going to do is use a table of Laplace transforms to go back and forth. So you can, if you take a look on page 317, line number 2, you will see the Laplace transform of e to the alpha t, and you will see something over here such that if alpha equals 1, which it is right here, the thing in front of the t is just a 1, you will end up with 1 over s minus 1. Well, that's pretty much it. If you understand the definition and you understand what we did over here, then you can see how you get back and forth from a function of t to its Laplace transform in s. We're going to use that table on page 317 a lot to go back and forth. And that in combination with the basic idea last time where you start off with a function of t, or with an equation, the differential equation of t, you move over onto the other side and you have an algebraic equation, the derivatives go away. As I said last time, when you take the Laplace transform, derivatives basically turn into multiplication. Then you have an algebraic equation over here, solve, solve, solve for capital Y, take the inverse Laplace transform, and you've solved your differential equation.